In this video, we'll take a look at how to draw all the possible structural or constitutional isomers for a compound of a given molecular formula. And just as a reminder, structural and constitutional isomers are the same. Those terms are just used interchangeably. And there's really three key steps in order to do this for any given molecular formula. And first, what you should do is determine the degrees of unsaturation, or the DOU. And the degrees of unsaturation, or DOU, is defined as this following formula, and this is how you calculate it from the molecular formula. So it's 1/2 of the number of hydrogens that would be present if the compound was fully saturated, minus the number of hydrogens that are actually present, minus X, which is a placeholder for a halogen, chlorine, bromine, etc., the group 17 element, and then add any number of nitrogens. Okay, so now the question is, well, how do we determine the number of hydrogen when fully saturated? That formula is defined as follows. It is 2 times the number of carbons plus 2. So for our specific example, we have C5H12. So to determine the degrees of unsaturation, we need to first determine the number of hydrogens that would be present if it was saturated. So we plug in 5 for C here, so it would be 2 times 5 plus 2. 2 times 5 is 10 plus 2 is 12. So fully saturated hydrocarbon with 5 carbons would have 12 hydrogens. That's exactly what we have present here. So now we can plug in this value into H saturation in our DOU. So we do that, so it's 12 minus how many are actually present, which is also 12, minus any halogens, add any nitrogens, neither are present in this compound, so it's just 12 minus 12, which is 0, divided by 2, still 0. So this is useful to determine first because DOU, remember, is the number of rings and pi bonds, and/or pi bonds. So if there was 2 degrees of unsaturation, for example, you could have a ring and a pi bond, and that would need to be considered when you draw the structural formula. Here we have no degrees of unsaturation. We don't need to worry about that complexity. So next, then, you want to determine all of the possible carbon chain lengths that you can have. So determine carbon chain lengths. Here, the easiest one to start with is 5 carbon chain. That would be the entire compound. So we can have 5 carbon chain. So 5 carbon chain. We can have a 4 carbon chain. This is going to have a 1 carbon substituent. We could have a 3 carbon chain, and that will have a 2 carbon substituent, or 2 carbons with, 2 substituents with 1 carbon. Now, you can't really have a 2 carbon chain, but we'll look at that because it's going to coalesce with what the others are when you would check if they're structural isomers or not. So this is a good useful point to notice that you just want to have the longest chain you can have and then the subsequent smaller ones that you would have different substituents. So then the last rule, or last step here, is what would the substituents be? Determine the different possible substituents and then place them. Substituents and place. So for this case, they're all just going to be carbon chain substituents. So they're going to be methyl groups or ethyl groups. So that will become clear as we work through this. But let's start with our 5 carbon chain. Remember, our formula is C5H12. And it's fully saturated, no pi bonds or no rings. So let's draw in the 5 carbon chain. All right, so this would be one possible structural isomer for C5H12 because we have our longest chain of 5. There's no more carbons that are necessary. This is one structure. Now, is there any substituent we can add to carbon 5? There is not, because there's no chlorine or some other substituent, only carbons. So if we were to add another carbon substituent there, it would no longer be C5H12. So now we must consider the 4 carbon chain length. So let's draw that. So now this is here where step 3 kind of comes into play. So we need to determine what are the substituents that we can have. We've already mentioned they're carbon chains. So now it's where can they go that it would be different than our 5-carbon branch. So if we put the methyl group that would be required here, the 1-carbon branch, if we put it at carbon 1 here, that is just going to make a 5-membered chain again, which is the same as what we started with. If we put it at 2, this is now different, right? Because this would be named 2-methylbutane. It has a methyl group on a chain of 4 as opposed to just a chain of 5. Now what happens if we put it at 3? Well, this is going to be the same, so I'll draw this for you. This is the same as what's drawn there because you would just number it right to left instead of left to right in the nomenclature. So that is our 2 distinct isomers so far. There's nothing else we can do with the 4-membered branch, the 4-membered longest chain rather. If you put it at this position here, it's also going to be just the same as the 5-membered chain. So next let's move to what's our third possibility, which is the 3-carbon chain. Oops, which is like this. That's our chain of carbons. Now, can we put a methyl group at 1 or 3 here, carbons 1 or 3, and we cannot, because if we do that will make it a 4-membered branch now, which is just going to be the same as what we have in step 2. So that means you have to put both of the methyl groups at carbon number 2. Now this would be 2,2-dimethylpropane if you were going to name it. And most importantly, you can just tell that this is structurally different than 2 because the longest chain is 3 with 2 branches. It still fits the formula, so that's good. So some of you may be wondering, well, what about an ethyl group? Can we place an ethyl group anywhere? Well, let's consider our 3-membered branch chain, which is the longest we can have and still have an ethyl group. Let's say we put the ethyl group here at 2. Well, this is now not different than anything else that we've had, right? Because now we would just number this. The longest chain now becomes 4. This is just another way of drawing 2-methyl butane, which is the same that we have in number 2. So the takeaway is you can do this as many times as you want. You're going to find that these 3 are the only 3 distinct structural isomers for a fully saturated hydrocarbon with a molecular formula of C5H12. All right, here we have another question. So again, we are looking to draw all the possible structural or constitutional isomers for a different compound which has a formula of C5H11Cl. Okay, so again, the first thing we want to start with is determining the degrees of unsaturation, which is 1/2 the number of hydrogens if it's saturated, minus the number of hydrogens actually present, minus halogens, plus nitrogens. So here, number of HSAT is 2 times 5, which is 10, plus 2, which is 12. Okay, so we go to degrees of unsaturation formula, we plug in what we just found. So this is 12 minus 11, that's what's actually present, minus 1 because chlorine is a halogen. So this is 12, 12 minus 12 is 0. So again, no degrees of unsaturation, which makes our lives a little bit easier here. We don't have to consider if there are any rings or pi bonds. So now we have to consider our chain length once again. So our chain length, again, is no different than the last question. We can either have 5-carbon chain, 4-carbon chain, or 3-carbon chain. Okay, so now the biggest difference is we have a chlorine substituent. So we need to consider where that chlorine can go on the chain. So let's simply start with the 5-carbon chain, as that deals with everything else except for the chlorine. So if we were to draw that, here's a 5-carbon chain. And let's say we'll start by putting the chlorine at the 1 position here. This is one suitable isomer. Then we can put the chlorine at 2 or 3. Once we put it at 4 or 5, that's going to be the same as 2 and 1 respectively, right? So 1 and 5 would be the same, 2 and 4 are the same, and then 3 is different. So we're going to have 3 different chlorine placements on the 5-membered branch, the 5-membered longest chain, right? Like these 3. Now, it's important to mention here that this second option here, so I'll label the distinct ones. So this second distinct structure is chiral. That carbon bound to the chlorine is chiral, this one. So there would be two stereoisomers, but it's important to keep in mind that this question is only asking for the structural isomers, so we're not going to concern ourselves with R and S, enantiomers of option 2. Okay, so this is all that we can have different for carbon, the 5-carbon chain, because we only have 5 carbons. So next we need to go to the 4-carbon branch options. Now, with the 4-carbon branch, you have several choices. So you need to put the chlorine somewhere that is distinct and the methyl group that is somewhere distinct. So let's just first start with what seems the most natural, at least to me, which would be put the chlorine at position 1 here and put the methyl group at position 1 as well. So if we do this, we have to notice what has just happened. Right? So by putting the methyl at carbon 1 of the 4-member chain, we've just now extended the carbon chain. Right? So this is the same as our second option we did of the 5-membered branch. So we cannot put the methyl group on the terminal ends if we're trying to make the longest chain shorter. Right? So we can still put the chlorine here at position 1, but the methyl must go at position 2. Because if we don't do that, the longest chain is just still going to be 5. With this, the longest chain is 4, 1, 2, 3, 4, and this is 1 chloro, 2 methyl. This is distinct from any of the ones at the top, so this is 4. This is our 4th distinct isomer. Now we can continue with having our longest carbon chain of 4, and let's continue with having the chlorine at the first position. So if we do that now, we know we can't put the methyl at 1. We just put the methyl at 2, so let's put the methyl at 3. Is this distinct? It is. Our longest chain is 1, 2, 3, 4. We have a 3-methyl group, 1 chlorine. This is distinct from everything else that's shown so far. Okay, let's continue with the 4-carbon chain, right, and the chlorine at 1, right? Well, actually, let's consider that. So if the chlorine is still at 1, the only other option we haven't looked at is at the end, which this is going to make the longest chain, again, 5 now. So we're done with the chlorine options at position 1. So the chlorine must now move somewhere. It can go at position 2, like this. And if we're going to do that, we have to keep in mind the methyl group cannot go at the terminal sides. That will make the chain longer. So it can go at position 2 as well. This is now a 2-chloro-2-methyl butane. This is different than everything else we've looked at. Okay, what's next? We can put the chlorine at the 3rd position, like this. That is different. Is there anywhere else you can put the methyl? Well, we know it can't go terminal, and we just did at position 2 and 3, so that is it for 2-chloro, the 2-chlorobutane series. What if we put the chlorine at the 3rd position? We'll notice that's just going to change your numbering system. That's going to end up being the same as the 2-chloro series. And we can't put it terminal either for the same reason, because that's going to be the same as 1-chloro. So we now must have to move to our 3-carbon chain, right? So if we have our 3-carbon chain, if we put the chlorine here at position 1, we have two methyl groups that we can place, right? So if we put the chlorine here at position 1, where can the 2 methyls go? Well, if they both go here, what is our longest chain? Longest chain is 1, 2, 3, or 1, 2, 3, or 1, 2, 3. So they're all 3. So this is a distinct structure. The longest chain, it would be a propane. Everything else we've looked at is at least a butane or a pentane. What about if we put the chlorine, if we replace the methyl in the chlorine? Let's consider that option. So methyl would go here, chlorine would go here. Now notice what we've done is we made the chain longer because we put a carbon on the terminal side of the chain, which extends the chain and does not make it a propane anymore. So this is actually the same as what's labeled as 6, because we would just number left to right in this case. We would number right to left in this case, and you'll see that these are the same. There's no other option for the 3 carbon chain. You can try them and convince yourself, but these are the 8 distinct isomers that you can have for C5H11Cl. And keep in mind, once again, we are not focusing on the stereoisomers. There are a number of chiral options here, but we are just looking at the structural different isomers. All right, here we have another question where we're asked to draw all possible structural constitutional isomers for a molecular formula of C5H10. So again, we should start with the degrees of unsaturation, which is defined as 1/2 the number of hydrogens saturated minus the number of hydrogens actually present minus halogens plus nitrogens. So again, the number of hydrogens saturated is calculated by 2 times the number of carbons, which is 5, plus 2, which is 12. Then we plug this value into our formula, degree of unsaturation formula. So it's 12 minus 10. No halogens or nitrogens. So 12 minus 10 is 2, divided by 2 is 1. So now we need to consider that there are options, there are structural isomers with a ring and structural isomers with a pi bond. And we need to consider all possible different options there. So first, let's start with the pi bond. So again, we need to consider our chain lengths. So we can have 5 carbons with the pi bond, we can have 4 carbon length with the pi bond, and we can have 3 carbon length with the pi bond. We also can have the ring. We can have 5 carbon ring, 4 carbon ring, or a 3 carbon ring. And then again, in the 3 carbons, there must be 2 methyl groups or an ethyl group. 4 carbon, there must be a methyl group, substituent. There must be a ethyl group or 2 methyl groups, and then a methyl group. Okay, so let's start with the 5 carbon chain for the pi bond. So we'll just draw our 5 carbon standard chain, looks like pentane, and now the pi bond can go in different positions. So we can start it at the 1 position. This is one distinct isomer. We can then put it at the 2 position, which is another distinct isomer. 1, 2, 3, 4, 5. Always check your carbons as you go. So now what's important with this is this can be cis or trans, but cis or trans, or E or Z, is a form of stereoisomerism. The cis and trans are diastereomers of one another. So that we're not going to consider those as different options here in the structural isomer type of question, because they're technically stereoisomers and not structural. So we're only going to consider those 2. Now, let's consider if we put the pi bond at position 3. Well, if we do that, I'll draw that just for clarity. If we do that and draw it here, like shown, you can just number this 1, 2 going right to left, same as left to right here. So these would be structurally the same. So these are all the options we have for 5 carbon chain containing the pi bond. Okay, so let's move to our 4 carbon chain. So here we have a 4 carbon chain. Again, the pi bond can go at the 1 position, but now we're missing a carbon. So the carbon has to go somewhere. It has to be a methyl group. It can't go terminal. Again, just the same reasons as last time, because if it does, it's going to extend the carbon chain, and it's now not going to be a 4 carbon chain, so it's going to be the same as one of our first 2 options. So that means we can only put the methyl group at the 2 or 3 position. So let's put it at 2. This is now 1 isomer, and then we can put it at 3, which is the other isomer. Right? Again, we cannot put it at 4 or 1 because that elongates the chain. So those are all the options you have for a 4 carbon chain. Let's move to a 3 carbon chain. So here we have our 3 carbon chain. Again, we can only put the methyl group they cannot be terminal. If they are terminal, it elongates the chain. So here, so again, we cannot add them terminal as this will elongate the chain, but here we don't have options really to put them not terminal, right? If we put one at position 2, one of the methyl groups, which we can do, and we have to do, this is now all of the carbon that can go at carbon number 2. We have to put the other carbon somewhere else. So let's consider if we put the other carbon here at this terminal side, that's going to be the exact same as what we see in number 3 here. But what about if we put it at carbon 1 like this? Well, now this is a 4-membered chain, like the chain is now no longer 3, but it is different than these other 4s because it has the 2 methyl groups attached to the alkene, which that is not present in 3 or 4. So this is another distinct isomer that really has a longest chain of 4, but the way I arrived to it as I worked this problem is the 3-carbon approach. There's not really a 3-carbon chain with the pi bond that is feasible here just due to the nature of the compound. So these are all the options we have for pi bonds with the different carbon chain lengths. Now let's consider our ring options. So we can start with the simplest form, which is going to have our 5-carbon ring. There's nothing that we can add to that, no substituents, so this just has to be cyclopentane as drawn here. There's nothing else that you can add. Now you can have a 4-membered ring, and there has to be 1 more carbon, so this has to be a methyl group. Now again, as I mentioned in the last question, this if there's chirality present, then you would have to consider that here. This has symmetry and is not chiral, even though it seems like this position may be chiral. You should always be checking for that. But again, even in the ones that are chiral, which we'll see a couple in the next example, but we don't consider that for different structural isomers. Okay, so next is our 3-carbon chain. Now our 3-carbon chain, we have 2 choices. We either have 2 methyl groups or a ethyl group. So I'm going to start with the ethyl group, as I think that is the simplest form. Now here, there's no other different choice, just like with option 7 here. If you put the methyl at a different spot, you're just going to start the numbering system at that substituent. So it's going to be the same regardless of where you put it on the ring. Now, for the methyls, it's different. So the methyl groups can go on the same carbon, like this. Now this would be a 1,1 dimethyl cyclopropane. Still, this is a chiral. But if you have 1,2, which is the other and final option, this is now chiral, and it can be cis or trans relative to the ring. Just like we have cis or trans relative to pi bonds, you can have that with rings as well. And this is going to be chiral, and you can have pairs of enantiomers. You can have RR, RS, and SS, all possible options for 1,2 dimethyl. But again, we're considering just the structural isomers. So these 10 are all the structurally distinct isomers that we can have for a molecular formula of C5H10. So as you can tell, going through the degrees of unsaturation is very useful for kind of guiding yourself through this process. The more degrees of unsaturation you have, the more possibilities that you have for different types of substituents and different ways to draw the structure itself. So you'll have to get a little bit more creative in the way that you approach this, but if you go through it systematically, like I've shown here, degrees of unsaturation, different carbon chain lengths, and the different possible substituents, you can rule out all possibilities as you go through down the line like this. So that is all I had planned for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a question or comment or any topic suggestion or anything like that, please feel free to leave it in the comment section down below, and I'll get back to you as soon as possible. So with that, I hope you have a great day, and I will see you all in the next video.